Coming up on this episode of the IoT Inc. Business Show.
The data is truth, right? Because it is what the system's actually doing. And any model is going to be some imperfect reflection of that. But the reason why I think engineering models or system dynamics models or whatever are so important is that they help provide paths to action and probably even better predictive power. So the data will give you a great snapshot, a very accurate snapshot of the current and previous state of a machine or a system. But it doesn't give you as much insight about how you extrapolate into the future.
The digital twin is a federation of data and models that can be analyzed or put into a simulation to create useful information about the past, present, or future of the DT's physical twin. The type of model and level of model can make or break the analysis or simulation. In this episode of the IoT Business Show, I get down and dirty with Jim Tung, breaking the digital twin down in order to understand this most important tech at both the atomic and system level.
All this and more on this episode of the IoT Inc. Business Show. The people, the business, and the technology of the next generation internet. This is the IoT Inc. Business Show. And now, here's your host, Bruce Sinclair.
Hello and welcome to the IoT Inc. Business Show. This show is made possible by sales of my book, IoT Inc., published by McGraw-Hill, and the IoT Inc. Certified IoT Professional, or ICIP, online training and certification program. Become a certified IoT professional by completing the program's 3 courses: ICIP Technology, ICIP Business, and ICIP Strategy and Digital Transformation. Details of which can be found at www.iot-inc.com. That's www.iot-inc.com. With me today on the IoT Show is Jim Tung. Jim is a MathWorks fellow focused on business and technology strategy and works with key customers and partners. Jim has been with MathWorks for 28 years and has over 35 years of experience in real-time systems, data acquisition, and technical computing. Jim, welcome to the show.
Thanks, Bruce. Happy to be here.
I've been doing IoT. It's kind of a running joke with my guests, and that is, I think there's still someone you're going to have a hard time beating, but that is, how long have you been doing IoT by another? It sounds like your experience goes way back there. Real-time systems, acquisition, technical computing. How far back do you think it goes, and when did you start calling it IoT, or do you even call it IoT now?
Well, I think IoT is kind of an abused term. I mean, we certainly have been involved with things, smart things that are connected things, for a long time. Probably I started MathWorks in 1988, and certainly in those days there were a lot of things that were connected to other things, either through field buses or industrial buses of different types, or RS-232, good old serial buses, as well as other kinds of defense and military buses as well. So before there was a widespread use of internet, we were certainly involved with it. And the analytics associated with that data has also been, something I've been involved in for a long time.
Yeah, and so are you saying that really for 28 years you were looking at these various buses and the data on them and starting to look from an analytics point of view?
Yeah, actually, before I started MathWorks, I was with other companies that did acquisition systems. So probably working with buses and getting data out of machines and industrial automation setting, as well as from a laboratory setting. That's probably going near on 34 years now.
Not 35.
Yeah, I know. I'll round downward just to be exactly.
Well, okay. Well, this is kind of a good segue. Why don't you then just continue on with it a little bit, and a little bit more about yourself, and in particular, when you're sitting into IoT and kind of what you do in IoT now.
Well, certainly. In terms of when we think about IoT, we're thinking about probably 3 different pieces of it. There's the edge devices and how much smarts you can build into those edge devices, how much data reduction, how much ability to respond locally can you build in there. And that's really an evolution of the whole embedded systems market. The second part is the aggregation of the data. And for us, that involves a lot of the disparate types of data that people are dealing with now. Some of it's business data, maintenance records, that kind of stuff. And a lot of it is engineering data. It could be images, could be signals, could be speech, could be machine data, and so on. And then the third piece is the analytics. With MATLAB, one of the core MathWorks products, we've been involved in lots of engineering analytics for a long time, whether it's statistics or frequency domain or whatever it is. And it's really just riding the wave of some of the newer, not newer, but reapplied and more powerful analytics now, such as deep learning. So when we think about IoT, we're really thinking about all three of those aspects of it.
No, that's three important areas. I'm interested to get your take on the analytics side. You're mentioning that you had done had a lot of experience in engineering analytics. How do you think different, or are they different? You kind of you're kind of talking about that a little bit, but what's your take on how things have changed in the analytics world?
A lot of the engineering analytics, which includes a lot of statistical, multivariate statistics, as well as the frequency domain and so on, that just continues apace. I mean, there are always new algorithms, new techniques for creating better, I'll call them data-driven models or analytics or transformations of the data. The interesting thing now, I think, is there's a merging or maybe a coupling of analytics that rely on the engineering insight about the system with others that are pure data-driven. So, 5 years ago, we would have researchers coming together who use MATLAB, and they'd argue about whether deep learning was even viable if you didn't know the physical system structure. And they were really approaching it from an engineering perspective. But today, I think there's much more of a view that the two can work very powerfully in combination. It's really a question of when to leverage the engineering know-how about the system and when to let the data speak for itself.
Well, yeah, let's talk about that a little. I think you bring up an important point, and you can kind of table it a slightly different way with respect to and analysts. So data science engineers and data science or data analysts and data engineers. You're kind of going in the idea that, so let's first define data-driven. So data-driven, maybe give us a quick definition of that, and then give us an example of engineering know-how, how the two can potentially work together.
Well, I think that when I think about data-driven, it's really a situation where it both includes the traditional statistical methods, but it is evolution of some of the traditional statistic methods where you're letting the data sets, both the input data as well as the observations coming out of the system, letting that dictate the characteristics of the model. And there is sometimes some structural aspects of it, but you're really, in many cases, letting the data drive the model definition. Now, in some cases, you're going to tag attributes of what you're observing. You may say, this is a cat, that is a dog, this is a bird, et cetera, so that the data-driven methods will have some supervision, some guidance from the person who's trained the system. In other cases, you're just letting the system figure out for itself, which is one of the attributes of deep learning, for example, with computer vision. So that's really what I would call data-driven. Engineering is when you're looking at the characteristics of the system that you know from an engineering standpoint, and you're using that know-how to try and understand how the system's going to behave. One of our customers maybe brings them together in an interesting way. So Baker Hughes, and this is a published story that we have permission to talk about. It's actually on our website. Baker Hughes, which is now part of GE, makes, among many other things, rigs that are used to extract oil and gas from the ground. And as they look at the predictive maintenance issues associated with those rigs, they actually had very little information, actually have had very little information about the machines because there are relatively few sensors associated with the status and condition of the machine. And so this particular customer started adding some sensors, some not willy-nilly, but sensors for all the different attributes, whether it's the time, the pressures, and different places of the machine, and so on. And they started gathering gigabytes and terabytes of data associated with the machine. And what they then started to do was to use statistical methods to say, and they also had records in terms of the maintenance records and fault records associated with machines. They knew when they were starting to go bad. And so they started by looking at statistical methods to say, okay, what will the statistics tell us about the association of the data about the machine and the eventual fault in the machine? And they found they were swimming in big data. So instead, rather than pursuing that route too far, they started looking at individual data sets as well as the nature of the machine itself and looked at individual data to say, what is the predictive power of individual sensors? Okay, what's the association of individual sensors with the result? Not only from a statistical standpoint, but knowing that certain valves are likely to fail in the machine and so on. And they're able to move down from, I think, 25 to 30 sensors down to 3 or 4 sensors that had tremendous predictive power. And at that point, they were able to apply both statistical methods, data-driven methods, as well as frequency-based methods, which were based on the understanding of the machine, and combine them to come up with essentially signatures, visualizations of the status of the machine to let the operator very quickly see the condition of the machine, how close it was to failure, how far it was going out of range, and so on. So that's just an example of sort of a combination that's probably a little heavy on the data-driven side, a little bit light on the engineering side to come up with the results.
No, but I like that one, Jim, because it does illustrate the two differences. I kind of like to think about it. I like to visualize data-driven models kind of in 3D. So like point clouds, and to recognize, let's just use that as, as the paradigm to try to recognize a pattern. Maybe it's even a face, maybe it's whatever the case. And then what you is engineering knowledge, but of course that could also be biological knowledge, that could be economic knowledge, that could be a lot of different, that's domain specific, to add additional insights to help you, and as in this example, to cut down what you're looking at, to maybe help you recognize what you're looking. But this is an interesting problem or question to me anyway, because even with all the engineering data, let's use the example of the oil rig and the sensors, at some point, doesn't the given model supersede all the engineering knowledge? Because once you've sampled it so many times, I would think that it would at some point be more accurate than, that started with. What are your thoughts there?
Well, first of all, I guess you made when I use the word engineering, term engineering, I do mean it in a very broad way. So I do agree it's biological and other types of systems as well. And the basis of a lot of that is a field that's I guess it's at the intersection of science and engineering in the undergraduate curriculum, which is system dynamics. Right? Systems just have dynamical behavior that are associated with them. But when it's taught in school, system dynamics is sort of an idealized field. Systems behave perfectly. So your point's well taken that, the data is truth, right? Because it is what the system's actually doing. And any model is going to be some imperfect reflection of that. But the reason why I think engineering models or system dynamics models or whatever are so important is that they help provide paths to action and probably even better predictive power. So the data will give you a great snapshot, a very accurate snapshot of the current and previous state of a machine or a system. But it doesn't give you as much insight about how you extrapolate into the future. And that's really where an understanding of the system dynamics, and so on and so forth are pretty important.
Yeah, well, let's peel this back a little bit. And everyone listening, you can tell this is gonna be pretty geeky and pretty techy interview today.
I'll try and keep it a little bit high level, but let's go. Let's
see where we go with this. So let's not conflate certain issues for our listeners. So we've got our original data, and we're going to call that the data, the original point cloud data. Let's use the analogy of we're just got in their point cloud. So we have the original raw data, what you're calling a data-driven. Well, maybe not. So then we got that data. Then we have contextual information what we're calling, system dynamics information or engineering data, kind of tells you, puts that point data, that actual data into context in some way or form. But then the third piece that I want to introduce into this is we now need to take that point data and fit it with something. We need to develop a model for it. And if we just use that, for visualization purposes, we're in a 3D point cloud, and let's pretend we're trying to see what face, then we need that point cloud with some mathematical models so that we can do some cause and effects on it. Because just with point data, it's terribly difficult. We have to abstract it. So with point data, it's difficult to abstract it and then go back in time, forward in time, or even during time, right? So there's three parts. We got our raw point data, we got our content, and then we have the model, right? And we're going to get to this digital twin pretty soon, everyone. But we have the model that is a representation of that point data and that contextual data, or hopefully that contextual data. Okay, how are we on the same page?
I would view it a little bit differently. Maybe we're using the term model in a slightly different way. So the data, I completely agree, that first point. The second aspect is that the model of the data is not only the context of the data, sort of the environment in which the data is operating or whatever, it's an assumption of what is generating the data. So maybe you're calling that the context, but it's the machine, it's the description of the machine that from which the data came or what is coming from. And it's not, the two aren't divorced, they're not separated. And so you need some ability, or you want some ability with that model of the system to be able to, people use different terms, calibrate it, update it, validate it, tune it, so that the model is a closer approximation of the data. So in fact, it's not a data-driven model, but it's a data-calibrated model, where that model still fits the physics of the system or the engineering know-how about the system, but it is improved and tuned based on the actual observed data. And once that model is updated and represents that individual machine, which is that whole digital twin thing, then that model can then be used to extrapolate into the future and have that predictive power that you talked about with your third point.
Okay, no, I think we're saying the same thing, or at least we're thinking. Good. And then let's just bring this to now something more concrete, and we'll move into means and the digital twin in a moment. But let's say the point data is simply what I was saying earlier. It's a 3D point, it's 3D scatter graph or 3D scatter graph, and it's supposed to represent, let's say we've got this grainy picture, and, like a movie like Fugitive, and we're trying to see who that person is. I don't know, and there's always it's funny, funky science when they do this. But let's say we have a point cloud, and then the model we're talking about is going to be the surface representation of the face and maybe how it moved, maybe so that we put a little bit of physics into that. So our point data is the 3D point cloud. Our contextual data, let's say, is, this is how it's got this pivot point. We've got some, rough relationships for the movement. And then our model is going to be, some surface transformation. It's going to be a transformation of that point data into a higher level representation. I think this is a key point, right? So that we can then do it. And that could be, what's going on at this point. Well, it's between data points, but we think since we've put a model on it, like let's say we put a skin on it, maybe that's the way to visualize it. This between this data point and this point, we have this one here, and it's going to look like this. How does that sound so far? Just trying to put it into something more because that's kind of what we're doing. We've got the point data, we're developing a model, we're using contextual information to help develop that model. What am I missing?
Well, I think, and in some cases that conversion of the point data into something that starts to become a face. Sometimes it's with knowledge of the data. In some cases, it's knowledge of sort of sensors. How do you, if you only have 5 data points, how do you fill in the other data points in between, right? I'm thinking back to my last time I watched Fugitive. And then all of that conspires to create a more full-fledged representation beyond what the data itself will give you, right? And then once you have something that's satisfying, then you're right. You can turn it into something that you can execute. You can call it a face. You can turn the face 40 degrees clockwise, and it'll hold together. And you can start to look at other data sets and say, is that a face? Is it the same face? And you can start to operate on things at a higher level.
Mm-hmm. Okay. No, good. I just think, just putting in the concrete will help everyone that's listening to this. But let's swing this now into the digital twin.
Mm-hmm.
I'm not a fan of the term, but I got to tell you that I'm now becoming a DT convert just because everyone calls it that. But let's move into the digital twin.
DT, not associated with politics, but with engineering concepts, right? Okay, just to be clear.
DT is in digital twin.
Got it.
I'm even using the acronym. I'm loving it so much. But what's your definition, Jim, of the DT? Let's leave it at that. What's the definition of a digital twin?
I don't really have a good definition of digital twin. I'm not a fan of it either, to be honest, because it is so used by so many different parties in so many different ways. So I don't want to just put my hat in the ring and sort of say, here's my definition and fight out with everybody else. I think there are a few aspects of digital twin that are important. One of them is that there is that real thing out there, the asset, the machine, whatever you want to call it. There's the model of that thing, that digital representation of it. And then there's the data associated, both the real thing and also with the digital representation of it, and sort of the coupling of all those three things. So those are concepts I think are important in underlying the idea of a digital twin, regardless of whether you want to define it or not. Another aspect, and one reason I don't like digital twin as a term, is that there's sort of this implication that it's just a single model of the real thing, that it is literally an exact replica, a single exact replica. But there are different models of the things that are useful for different reasons. And so I tend to think of digital twins as a composite of different types of models, maybe of different aspects or different pieces of the real asset that can support decision making and prediction and other analytics for different purposes. So there's no one size fits all when it comes to the models associated with digital twins.
Yeah, no, I think you bring up a good point. And I've been kind of trying to, as we're going through this series, I've been trying to refine definition more and more. And I like what you said, because I think some people kind of say there's a digital twin or there's many digital twins. I'm saying, listen, I agree with what you're saying, or maybe I'm just putting a different spin on it. But a digital twin is a federation of many models, And twin, in my view, though, however, is more than just a model. Really, I think a simulation. That's what I'm coming. I don't know what you think about that, but I'm coming to that realization, or I guess I'm sort of getting led there, or at least that's where I am in my journey. As a digital twin is a simulation, and it consists of a federation of models and associated data, and that data is going to be the raw data like we were talking about. That can come from sensors. It can also come from external systems. And then a very important point that you put out there is also the data that comes from the actual asset itself, or the thing, I guess in this case, that we're talking about. How does that ring for you? I'm saying it out loud as much just to get your feedback as I am kind of what it is.
I agree with you. I mean, I think when we think about models, there's some models that you cannot simulate, and then those are almost just pure descriptive models where you can't do anything except understand the description. But from our standpoint at MathWorks, models really have power when you can simulate them. And so I don't think of the digital twin as the simulation per se, but I think of it as that federation of models that you can run different simulations of, because different models simulate in different ways. So even then, a digital twin is not a simulation, right? It's right? Exactly for different purposes. And one of the things, when people talk about digital twin, one of the ways that people often break it down and have recently is they're data-driven models they can simulate or put together and project forward, and then there are these physics-based ones. And I never quite understood what people meant by physics-based models, even though we're sort of in the field. And the reason I get confused is because the example people usually talk about are the kinds of models that are finite element based in terms of simulation. And those are great, but they're great for components. They're great for the lower level, very detailed kind of analysis of particular pieces.
And in particular, there's a structural analysis.
Things that involve geometry and structure.
Other purposes too, like flow, so forth. But in this case, it's even very specific to a structure, right?
And the insight versus the compute time. That how much insight you get per compute time is pretty low, right? Because you got to do a lot of simulation. You got to crank through a lot of computing and do a lot of simulation to get the insight. Now, the insight in many cases is worth it for a particular component. But the thing that the type of modeling that we think is a complement to that type of finite element based simulation is more of a system level simulation, a system level model, where you have less detail about the various pieces of the system, but the system level model stitches those various pieces together and says, how does this series of connected components behave over time? So it's really a focus on time as opposed to the structure that you talked about.
Mm-hmm. Yeah, no, I mean, I agree with you, and let's dig into this a little bit more. I think finite element so now what we're talking about, just to put things in context again, is the mathematics that we're using to make a model out of this original, let's pretend it's this cloud. So what you're saying, Jim, is physics-based model is generally associated with a finite element, an FEM model. And I agree with you, because I think there's certainly areas where finite element analysis is super appropriate. It makes a lot of sense. However, trying to use for other purposes may not be that fruitful. And we had someone else on the podcast from FEM that recently acquired FEDM, and they to accelerate these FEM calculations so they can be done in real time. But I think what's important, at least my view, and I want to talk about it to you, is it's important to choose that correct underlying mathematics of that model for the appropriate phenomena that you're measuring. So in some cases, an FEM would be just perfect. But in other cases, I don't think it's a general physics-based model, because that's just one type of physics. It could be a mechanical system. It can be a dynamic system, same thing. But you know what I mean? It could be a Newtonian system. So I guess this is a long-winded way of saying I believe it's important to choose the right mathematics to represent the model, because different mathematics, whether it's FEM for certain things and others for others, are going to be more attuned to that particular phenomena. What do you think?
Well, I think I think about less about the phenomenon and more about the why does an organization want to do digital twins, right? If you have a real running machine out in the field and you want to keep pace with it, with the digital representation, and say, is it continuing to operate normal? That's sort of a holistic question about the system itself. It's not saying is the particular valve or is the particular structural element behaving correctly. You're saying is the system behaving correctly or behaving as I expect? Mm-hmm. And that kind of overall diagnostic, I think, requires a certain type of simulation, a certain level of fidelity or lack of fidelity in terms of the models. And once there's a determination that a system is not behaving as it should, then you may enter a diagnostic mode to say, what are the suspects? What are the causes for this potential misbehavior? And at that point, you can enter a different type of model, a different type of simulation. Finite elements is perfectly appropriate. But as you say, finite elements, you've already chosen the piece you care about, and you're investing a lot of time and energy to analyze it well, regardless of whether it's real time or not. You're narrowing the focus already. And so I think the methods of system level modeling, of the what I'll call finite element based modeling, because I think people tend to associate closely with the term physics based, correctly or not. I think the two do complement each other, and I think that's an important aspect. But when you're talking about optimizing a system, when you talk about optimizing a system, you're really talking about optimizing usually at a system level. And so optimization often requires something that lets you look at the different attributes and sort of do the trade-offs of tuning them to get the optimal result.
Yeah, I agree. And I think you bring up an important point into the conversation, and that is the system level. Before we go there, you're right. Let's start at the fundamentals. And why are we using a digital twin IoT? Well, we're using it to look present, right? To see if things are working properly. We can use it to look in the past, maybe just ask questions of what happened. Why did this happen? And we can use it to look into the future, right? We can say predictions. Now, what you're bringing up here, which I think is very important, is the level of, I don't know if the word fidelity is right, but I guess maybe a higher way, the level of fidelity. And a lot of the insights, I think what you're saying here or postulating is a lot of the insights can be found at the system level. But if we think about, and I'm going to see, it's a never changing definition, but if we think about the digital twin as a federation of simulations. Well, if we look at organizations, then really they're nested simulations, right? They're simulations of simulations. So the sim level, now you could look at it as from BOP and do and go all the way from the parts to products to how they interact as a system, or you could represent a higher level. And I think what you're saying is, and I don't want to put words in your mouth, but I think what you're saying, we're looking at it from this particular vantage point, that there's a lot of not going into the minutia and looking at a high level, at a system level. So what are these concepts here?
Well, let me describe one customer that maybe brings that a little bit, as you say, makes it real. One of our customers is an operator for a fairly large electrical grid. Okay, so we're all talking about smart grids. We're all trying to say, okay, given different loads, how's it going to modify its behavior so that I have clean power and it's always up and I never have brownouts and blackouts. And they care about the overall electrical network. And so they're looking at things with fairly broad span. What they do is they put together a system that takes data from the real network, all the different pieces of equipment that actually are switching and managing and balancing the load on the real network. So they're gathering information from the real grid about every 5 minutes or so. And they use it to calibrate or update a model of that entire grid. And that model includes the transport of and distribution of the energy. It includes the HVDCs, the various components that sort of do the switching within various pieces of the network. And they use that real data to update that model. So the model is a good current representation of the current state of the network. They then run simulations looking forward into time, and they do this every 30 minutes. They run simulations looking forward into time to say, if these particular pieces of equipment failed, do I still have enough reserve power to last in order, based on what regulation requires, based on what the rules on me as an operator require. And so every 5 minutes, they're getting the data and updating the real model. And then every 30 minutes, they run projections going forward to say, what do I have to change about the operation of my electrical grid so that I always have enough reserve power? Now, the model that they're running is, in fact, as you say, a composition of models. In some cases, pieces of models, like models for pieces of the equipment, actually are coming from the vendors of the equipment. Right. So they know how the equipment works, and in many cases, they use the same models to actually build the equipment. So they provide the operator with slightly generalized models of the equipment, and then the operator can then take those pieces of model and compose them with other pieces of model and come up with a good overall representation of the network. So composability is an important piece of that type of modeling approach.
Yeah, no, that's a great example, actually, and I like that it's real. And, one way to call it, they were looking forward is predictive, but also I think what you're indicating that, can we change? Is there anything we can change today so that prediction doesn't come true? And that they call that prescriptive, right? That's prescriptive.
Yeah, absolutely.
But also the reason I like this is to kind of drive home another point, and we were just talking about this. Now, really what we're talking about, everyone, is we're talking about coming up with a data science strategy or data analytics strategy. That is, what are the levels of the models and simulations that we're talking about? Like what you're saying there, Jim, some of the components are modeled, or maybe all of them are, and they get some of them from the manufacturers. But a high-level representation of that grid also needs to be there. Or I would argue, and I'm kind of arguing for what you said earlier, maybe, but I could see, instead of using an FE model, in this case, we go back to linear algebra and it's a directed graph model. And this is an example using the right math for the underlying to, I guess, inform the analytics when looking at data, right? Because really we're looking at sources and sinks in a way. I'm really high level, right? But I would argue that while it's important to roll up all the emulations, there's value, like you were saying earlier, also looking at it at more of a system level, and that might be a completely different model. I think what we're talking about here, in a sense, is our strategy of how we're going to package the data and simulate the data. What do you think?
I think that an important aspect of the system model is that it is not divorced from the data. I mentioned earlier one example, which is the data being used to calibrate the model and so on. Another piece, though, that's people don't often recognize is that if you have a part of the system and you don't have a good, I'll say, mathematical model of it, but you've got data about it, historical data that's been collected from the real machine, then the data itself can become part of that simulation. So if you don't have a good model that you can trust for a portion of the overall system and its context, then use recorded data as a part of that simulation.
No, absolutely. Absolutely. But let me, because I just want to make sure I'm getting confused. So I want to make sure that I clarify this. When you say we have a model but maybe you can use the original data, what do you mean if we use?
Let me change context. In automotive, today everybody's thinking about how to create autonomous vehicles and how to make them more and more self-driving and different levels of autonomy and so on. They use modeling as a key piece of that to say, what are the sensors going to provide me? How do I transform the data coming from these radars and lidars and all this kind of stuff? And how am I going to engineer and design my system to make the right decisions and to take the right actions, right? And so a lot of the design there involves models of the system. But at the same time, everybody who's designing autonomous vehicles have test vehicles all over the place that have been collecting millions and millions and gazillions of miles of data from real vehicles in real situations. And so in some cases, you're not going to want to have models of driving scenarios, models of what a camera sees as it looks down a road. You'll also want to take real camera data from the millions of miles of collected information and run simulations of your perceptive car with real data being piped through that model of the perception systems. Yeah. Okay. And so it's less about data about the system itself, but in some cases, it's data about the environment or the inputs into the system and so on that you want to leverage real data for.
Yeah. No. So this is where I just want to clarify. Using the real data, my assumption would be that you would use that real data to come up with a model. Not that you have that model originally. So maybe you've got the original contextual model to try to go back in the thread that we were talking about originally. Maybe we're that like a contextual model of this is a road that we're looking at. There's generally sidewalks, maybe there's trees on the side. And then we've got the raw data. However, to execute that raw data model, we still need to put that raw data form that will be executable. And that is what we were talking about earlier. It's an FEM model, which I don't think is appropriate in this case. It's not a linear algebra because I don't think that's appropriate in this case. I don't know. It would be maybe just
It could be a deep learning, a network, neural network used in deep learning, for example.
clarify, when you're using a network for deep learning, at least my understanding is that what you're doing is you're using deep learning to come up with the right parameters to create that executable model, right? And so
yes,
tool,
right,
right, to create that model. And so it's still at the end of the day, just to peel things back and to have the different parts, we've got the original data, then we've got a model that we've used some mathematical form, FEM, linear algebra, whatever the case. In case, I don't think it would be those, and the contextual model. So I think we're still talking about the same, whether we're calling them the right word, I don't know, but we're still talking about those same three parts, or is there more in your example?
Well, I think that there's the data, there's the deep learning or whatever method, or approach for constructing that contextual model from that real data. The result of that deep learning technique is a network, and the network is the executable model.
Okay. Yeah, I like
that. If you then feed it new data from a camera, it'll tell me this is a road. This is a road with a pedestrian. This is a road with a pedestrian going this direction, et cetera, et cetera. Right. And so the thing about deep learning, though, and a lot of the data-driven techniques is that they're only as good as the data that they're trained with. But they then have to operate in situations that they weren't trained on, like driving. And so you then want to take all this recorded data that these automakers have that the system was not trained on, and basically test the system against all these different scenarios that you know exist because they've been recorded, but the system was not designed to address.
Right. Yeah, no, I like that. And I like that what you're saying is Alt is a network model, right? And then that's the executable, and then it's using the real world data coming from the video, let's say, and then this is not in a literal sense, but projecting it onto this network model to make decisions.
Or to at least make perceptions,
to inform decisions.
Yes, exactly.
And then this is actually, and I think the underlying point that you're making here, or at least one of them that I'm seeing, is this using deep learning. It's assisted deep learning, and so there's a little bit of controversy of, will deep learning be able to take the place of a domain subject or expert, whatever term, subject matter expert.
Like subject matter expert or doing,
And I possibly know. I think that there is that training that's necessary, but then at some point, it's like you're saying, then it has to be let out into the wild. But I think I still think until we've got the computational power from a zillion different directions, I still think you need to inform or guide that deep learning because making those connections is really difficult. And
I think the thing with deep learning is that you don't guide deep learning, right? Because the whole purpose of it is that it's unsupervised. So deep learning gets better and better, leads to network models that are better and better the more data they're exposed to. But when you're building systems like cars, it's not a question of is it better and better. The question is it good enough? Is it good? Is it satisfied? Is it acceptable? Can I give it a driver's license? And so I think the challenge or the opportunity there is to take the data science approaches and to couple them with the domain experts, because the domain experts will both know how to build safeguard systems that will work, or that will know when the data-driven approach isn't behaving the way it should. So I think the domain expert is a good complement to the data science or the analyst. I think in many organizations, there's been a tendency to sort of leave them somewhat separated in how processes get defined or analytics get created. And we're always trying to take our customers and make sure those groups are in the same room talking to each other, because yes, data will represent a lot, but know-how about the system does as well. And as long as they can have the right conversation in the same room, they may use different techniques, and they may apply them to different parts of the system design or the system behavior, but it will lead to a better system.
Yeah, and maybe an example would be you have a deep learning system that's observing the moves of a board. Now, eventually, without any guidance, let's say that you're looking at or you're looking at, maybe that's not a good example. I'm trying to see, to help deep learning system understand its chess versus chess. I guess the same. The board is the same. Then we might need to point the deep learning in a certain direction. Or are you saying that you don't even point it in any direction, just let it go, and it just sort of comes back with what it comes to the role, isn't it? The role of the subject matter expert is to point that deep learning, not to guide it. Maybe that was the wrong term, but to say, look in this direction, because it's infinite directions. Unless maybe that's a concept I'm understanding with deep learning. Maybe it's able to look at the infinite. It just seems to me that you would need to at least point it directionally somewhere.
Well, I think the thing about deep learning is that the different layers of a network model will inform different parts of the perception. They'll extract different features. And the nice thing about deep learning is that that layer of the network will figure out for itself how to organize itself, how to do the weightings so that it can extract features effectively. Now, one aspect of deep learning and of that whole approach is if I then want to take a network model that's been trained for one purpose, pets, determining what kind of an animal it is in my photos, and I want to take that same model and use it to identify foods off of menu, from a picture-oriented menu. I may just yank out certain pieces of the network and say those are no longer valid. And that can take some domain expertise to say, okay, that level of feature is no longer appropriate. But at that point, I'm going to yank out that level of that piece of the model and then let the rest of the model retrain based on this new data to do that task. Read the food menu instead of identifying pets in a photo album. So, there's probably some domain expertise that's useful there to know what parts of the model are no longer relevant, and so I can retrain the model based on this new data set, based on new assumptions.
Maybe so. It's a combination of those assumptions and the knowledge that helps them. But fascinating. But let's move up a couple levels on the stack, and I just want to, as in time, because we've been going real deep, but I want to now make this a little bit more pragmatic. All right. So how would listeners or, their data scientists or their mathematicians use MathWorks to create a digital twin and then to use that twin? Maybe just take us, just the mechanics of what has to be done.
Okay. Well, there are two core products that we have at MathWorks, MATLAB and Simulink. So MATLAB is strictly well-tuned to the data-driven approaches, the analytics, the deep learning, machine learning, statistical methods. And so MATLAB is a high-level programming language, but one of the things we've done is you can either work with it programmatically if you're comfortable with MATLAB and you learned in school, that sort of thing. But we also have apps. They're point-and-click applications so that you can build classifiers, you can do regression and all that kind of stuff just by pointing and clicking. Typically, what you're going to do is you're going to identify data sets that you want to use as input into your, let's say, regression method or deep learning method or whatever it happens to be. You'll identify the data sets. You may have some cleanup, get rid of noise, that kind of stuff. And then you can either programmatically or with these point-and-click apps in MATLAB go through the steps to generate that data-driven model. And it could be statistical and regression-based, it could be deep learning-based, and so on and so forth. There'll be different apps for different purposes. And the result of that is something you can then compute. You can put up in the cloud, you can put onto an embedded device, that sort of thing, as you see fit. Essentially, it's a classifier or a predictor that you can then move outside the MATLAB environment and put whatever you want, wherever you need that capability to go.
Once you've found that model, right?
Once you've found the model that is satisfactory in its performance.
And that's a big part of it, right? So what we're talking about is old school ETL, extract, transform, load, execute, and what we're doing in MATLAB to try obviously find the data that we need to be working on, massage it if we need to kind of equalize it with other data, for lack of a better word, and then execute on it. And that execution is going to be based on the model that we think is best fits. Let's use that as a term. Right? Yep. Okay.
Right. And the data could be heterogeneous. It could be individual data points from a machine or a system. It could be images, et cetera, et cetera. Simulink, which is the other core platform we have, operates pretty differently. It's more that system level modeling tool. And so it's not a programming language. It's a block diagram environment in which you will drag component blocks onto a canvas, and each block represents a piece of the system. It could be an electrical component, it could be a mechanical component, it could be a piece of math, it could be lots of different things. And then you wire them together, and in doing that, you're essentially describing the interaction or the connectivity of that system, of the system component. And so it's essentially drawing the it's not a physical schematic, but it's sort of drawing of the pieces of the system and how they connect to each other. And once you have that connected graph or that connected block diagram, you can simulate it. You can say, let me run it for the next, 2 hours. Let me run 2 hours of simulation time and see how it behaves. Now the nice thing about the system components is they could be abstract and idealized, so these linear things, or they could be very nonlinear, very real world descriptions of sort of the very nonlinear attributes of something, operating in friction or with air resistance, that kind of stuff. So these can be very sophisticated behaviors.
Okay, so what I'm understanding, and it kind of maps onto our discussion earlier, you got your MATLAB, and where the simulation is happening there is that you're first finding the model, and then you're outputting, that's point and click or programming, whatever the case may be. What we're trying to do is find that appropriate model. And then we're outputting code, I guess, right? Executable that could run in the cloud on the embedded device. It could run somewhere. And then that code is if that model, the code of that model to create a simulation is done by the application, right? Because it needs to then exercise that model.
Well, it could be in a couple of forms. So if you have the model in that case with MATLAB, MATLAB is the executable. It's the application that's going to run the code. And you can take MATLAB and you can put it up in MATLAB in the cloud and AWS and so on and so forth. So MATLAB itself could be the way in which you deploy it. Alternately, you could, from MATLAB, generate C code. And the C code gets compiled and gets put wherever you want to run it. And at that point, the C code is going to include, it will be the model. And yes, you would then have something else that's calling that executable to say, run this compiled C code now.
And so I kind of think of it, kind of like a video game where the model is the valve player and then the simulation is the game that it's in, and then that may include other players, the ball and so forth. And the difference with Simulink, though, this is what I'm trying to understand. Number one, I get it at a higher level, so it's modeling systems, which will be very important for certain types of IoT applications. And it's a model and the simulation. Maybe just tease apart the differences between how we're using then Simulink in our IoT product system environment versus how we're using MATLABs or the code that MATLAB generates.
Yeah, in the case of Simulink, you're putting together the model in advance, okay, based on an understanding of the
you're wiring
pieces of the physical. You're wiring it together, knowing what the pieces of the physical system are, where the components are.
The output of one is the input of the other, or this affects this.
Exactly. But the particular component may or may not. Okay, so once you have that all put together, then the Simulink solver, which is the executable, which is the application, whatever you want to call it, is the thing that actually makes it go forward in time accurately. Okay, and so the solver is really inseparable from the model description when you want to have an accurate time-based simulation. Once you have a good simulation and running in Simulink, then you again have the ability, as with MATLAB, to generate code, and it's very commonly used in Simulink, to generate code of the system, maybe particular algorithms, maybe of the overall simulation. You generate C code, again, for example, and you'll then run that maybe in a real-time computer if you want to do testing or real-time simulation, or you want to embed it into a device of some sort. Okay. So again, the flow is quite similar, and perhaps the embedded flow is much more common in Simulink than even with MATLAB.
But if we're to squint our eyes we're kind of doing the same thing with both products. However, one is better suited for, let's call it data-driven, and the other one is better suited for a system model. Is that accurate?
I think that's correct. And I think the other part of a system level model is that different pieces of the overall system as we talked about earlier, it's going to be a composite of different models. Right. And a model of a particular piece may not be expressed in Simulink. It may not be modeled in Simulink, but you want to include it in a Simulink simulation. And so one of the things that's important is to be able to take models from different types of tools, that aren't Simulink, and integrate them, compose them, so that pieces can come from different places and be from different parties, and you can then integrate them into one platform and then orchestrate how it all is going to behave together.
Could you take then the model that's produced by MATLabs and put it inside one of those blocks of Simulink?
Yes, absolutely.
So for me anyway, how I'm interpreting what you're saying is that, it's just like I said, it's kind of the level, and it was what we talked about earlier too, where there would be a lot of value in some situations, and I would think almost all, because products pretty much are all systems, they're systems of systems. There's a lot of value in a higher level model rather than the low. Well, there's different value in a high level model, lower model, and I think what we're exposing here to everyone listening is, again, coming down to that data science strategy. What is it that what are you trying to do? But we're just trying to, I think what we're exposing in this conversation is that there are types of models and simulations available to the listeners, and they have to understand them. They have to understand what they're trying to achieve, but it's just one size fits all. And in fact, it's kind of, a block, like a block view versus a micro versus a macro view. And they both provide different types of value. You might use them both, but I think that's what I'm getting from what you're saying. Does that ring true to you?
Yeah, absolutely. And they could be used by different groups who want to look at different aspects of a system and be used in parallel, or in fact they could be combined. Yes. So I mentioned that finite element and component level modeling has a particular value. You can bring these models into Simulink and sort of have both a broad time-oriented view of the system, but then at each time step say, what is this structure or geometry doing? So they can be combined in very interesting, in some cases very powerful ways, depending again on what that overall objective is.
What you're saying, Jim, I think, is you're describing that federation of simulations that we talked about earlier, aren't you? Absolutely.
Yep.
Yeah. All right. That's an awesome place to leave it. Excellent. Good. We've dove right down, and I came up to at least help people first understand the details and the importance of the math and the different types of math, and also the importance of the different types of levels that you're looking at the data, the macro versus the micro, and the relationship between them. Where can people dig in even further? Maybe find out more about you, or obviously MathLab?
The best place is our website. So if you go to MathWorks.com, we have a lot of different kinds of information. What I typically suggest is people just go to the search box. And for people interested in this area, probably a few phrases might bear the most fruit. Data analytics would be one. IoT would be another. And probably predictive maintenance would be the third. I think those will slice through different parts of what we have to talk about and what we have to offer, and I think provide three good lenses on it. Then, of course, based on what you find there, just keep on digging and looking for more.
Well, we'll include both the link and the search phrases in the show analysis notes. Jim, excellent. Very much enjoyed the conversation. Thank you.
Same here, Bruce. I really appreciate it.
Okay. That was a great talk with Jim Tung of MathWorks. This podcast goes vertical, deep diving into different topics each week. If you prefer a more horizontal and structured approach to learning IoT business and its orbiting technologies, check out my book IoT Inc., published by McGraw-Hill, or become a certified IoT professional by completing the ICIP training and certification program. For details, just go to www.iot-inc.com. Also go to www.iot-inc.com for an analysis of this episode, links to things that were mentioned during the episode, and very importantly, the episode's PDF transcript. Just search for the name of the episode or the guest. If you're new to this podcast, subscribe. That way you'll get every week's episode delivered straight to your device. Or, if you've been listening for a while, there are 3 ways you can support the show. You can leave a rating or a review on iTunes. Just go to iot-inc.com/iTunes. It only takes 1 click to leave a rating, a little bit longer to leave a review. You can share it on social. I'm on LinkedIn, to a lesser extent on Twitter. And of course, you can support the show by buying my book, IoT Inc., or the ICIP training and certification program. It's how I pay the bills. Next week's episode is the emergence of the IoT cognitive digital twin with Ahmed El-Adi of Accenture. I hope you can join me then. I'm your host, Bruce Sinclair. Thank you for listening. Till next time, may your path to IoT business be a mirrored one.
You have been listening to the IoT Inc. Business Show.